Philip, thank you so much for joining us today. We're honored to have you. And I'm pretty sure that this webinar will provide amazing insights to this audience. So before you jump into your presentation, would you like to introduce yourself?
Yes, absolutely. Let me maybe start sharing, and I have a slide for introducing myself.
That would be great. Oh, and one more thing that I will let people know. A gente vai gravar, tá, esse webinar, então se por acaso vocês não conseguirem ficar até o final, não tem problema, tá? A gente vai mandar um e-mail depois para todo mundo que se inscreveu com essa gravação, tá? Okay, you can go ahead.
All right. So thanks everyone for joining and having me. Switching to English now. And what I want to do today is to talk about the use of computer vision and deep learning to enhance medical diagnostics. So to introduce myself, my name is Philipp Singer. I live and I'm born in Austria, currently living in Vienna, which is the capital, and it is in Central Europe. I have a history of working in both academia and industry. So I did a PhD in computer science, also in an Austrian university, and I also did a postdoc in Germany. After that, I switched to industry. I first worked in an insurance company as a data scientist, and now for around 1.5 years, I work as a senior data scientist at H2O AI. So yeah, given this history of mine, both in academia and in industry, I would say that I have quite some profound experience in machine learning research and applications. And I want to talk a little bit about this experience today throughout this talk. And I am also actively, or have been actively participating on Kaggle for around the last 3 years, I would say. And I am a Kaggle competitions grandmaster, and I have been until very recently ranked first in the global leaderboard, and I'm currently ranked third. And actually throughout this, as you are also participating in a datathon, I thought I'd take this chance and also talk a little bit about Kaggle, because it could be useful for giving you inspiration. And I will talk then more about medical image problems, and also talk about a few use cases I have worked with in the past, which also stem from competitions being done on Kaggle. So just a very quick intro. What is Kaggle? Kaggle is calling itself your home for data science. It is an online community of data scientists and machine learners. It was founded in 2010, acquired by Google in 2017, and it is most well known for its data science competitions. But it also has a full community around it for sharing notebooks, sharing information, ideas, discussions, data sets quite maybe relevant for participating also in a datathon. But it also has courses, tutorials, and a full infrastructure for free notebooks with CPUs and GPUs. But why am I mentioning Kaggle? As I already kind of hinted towards, it can be a great resource for inspiration for you. And there have been quite a few medical image related competitions held on the platform. So they have interesting data sets and also interesting insights from participants in these competitions. So whatever I'm telling you now is just a small set of insights you could find by researching more on these problems and delving more into what others have been doing. So just a very quick glance of my history with data science projects and specifically my Kaggle journey. So as you can see here, I have been quite active in these types of 1 to 3 month long competitions that have been held on Kaggle. And I have been doing quite well. So this is just my best set of competitions I have been participating in. So all of them have been either, so you can see that I have won 7 competitions and have been doing very well in many others. And what I have always been trying to do in the past is to really do different types of problems, so really tackle different types of problems. So for example, doing image competitions, audio competitions, text competitions, tabular problems. And I think this is really the beauty of machine learning in general, is that you can try to tackle with similar techniques and methods so many different types of problems. And you can also apply techniques from certain types of problems to other types of problems. You see no connection at first at all. So for example, I participated in NFL, so American football related competitions. And as you can see, did really well, but I personally had no expertise in the field beforehand. So I'm just saying this so that you don't feel overwhelmed, that you could find good solutions, for example, for medical image solutions, even if you have no medical expertise per se. While I did a lot of other stuff, what I want to do today in this talk really is to talk about medical images. And I want to capture a few of the projects I have been doing in the past. And just to give you kind of idea of how to approach this kind of problems, and also to hopefully inspire you a little bit for your journey. But before we go into use case related projects, let's rather take one step back and start with what is artificial intelligence for medical images and why are we even doing it? So first, the main concept of is to apply computer vision techniques to medical images for diagnostics. So I'm saying diagnostics here, but it could be more, right? But diagnostics is usually the main use case you find. So the goal is to, for example, recognize different types of disease patterns, lesions, biomarkers, or other medical irregularities in images. So if you would have a chest X-ray as exhibited here on the right-hand side, the task of the AI would be similar to what a human does, is to find irregularities, for example, in this image and automatically predict and detect them. So it is the automatic analysis and recognition of different of these types of patterns. And why is this relevant nowadays, or has been relevant for the last couple of years, is because we have such a rapid development and research in the area of deep learning for computer vision in general. And because we have this strong research and developments throughout the past few years, not related to medical images, it is still driving a lot what we can do nowadays in the area of medical images. And before we go further, let's again take one step back, because I have been now mentioning deep learning, computer vision. What is deep learning actually? Deep learning is a subclass of machine learning, and it is usually based on deep neural networks. So why is it called deep? Because these neural networks have multiple layers in deep learning. So on the bottom, you can see, like in the 1980s era of neural networks, you usually had very shallow networks with like one hidden layer maybe, or maybe two. And this was mostly due to the restriction of computing power and good algorithms to train these models. And then throughout the last 10 years or even 20 years, we had a huge acceleration in computing power, which enabled us to train better and larger of these types of deep learning models. And the common goal, so you have multiple hidden layers, and they try to process hierarchical features. So the goal, so kind of the summary goal oftentimes of deep learning is to progressively extract higher level features from raw input. So let's say you have this input image here, and then you have multiple layers. And this is just a very rough abstraction. And in reality, this looks, of course, a bit more complex or intervened, I would say. And you could say that some certain areas of these networks are able to identify different types of patterns in the image, for example, like light and dark pixel values or edges, combination of edges, features, and then you combine the features and try to predict something. And this is really kind of the ground structure of how these deep learning neural networks work for image type of problems. And there has been a breakthrough in applications to these new types of unstructured data, like images, text, audio, video. And today we talk mostly about images. And the next thing why this has been working so well in the last few years, and specifically also has been working well for medical images, is the concept of transfer learning. So the idea of transfer learning is that some certain architectures of these networks are first trained on very generic data sets. And there is the most common one for that task is called ImageNet, which is just a data set of very generic images, let's say a person, a car, and so on and so forth, with certain types of classes. And the model is trained on that task, and the model and the architecture weights learn to identify, for example, different types of shapes in images, edges, and so on and so forth. Then you take these pre-trained models and you what is called fine-tuning. So you train them on your data set at hand. And your data set at hand could be a chest X-ray data set. But it is already starting from a better point in terms of weights for that already has trained a more generic task beforehand. And that means that for your task, you can fine-tune it on your task, and you would need less data than you would need if you, for example, would train it completely from scratch. And there is constant improvement and research on these pre-trained architectures and models. So every day some new stuff is coming out. And here on the right-hand side, and this graph only goes from 2010 to 2017. So now imagine 3 years further, you can see kind of the process we have been achieving over this time period on this ImageNet data set. So in 2010, this data set first came out, and there is also a yearly competition surrounding it. Every team got at least 25% wrong of this data set. So of 100% of this full data set, 25% was wrong for each participant. And in 2012, the first team achieved to get an error rate lower than 25%. And in 2017, most teams had less than 5% wrong. And we are constantly improving that. Of course, we cannot make the jump from 25 to 5 any longer, but it is now about going from 5 to 4 and 3 and so on and so forth. But you can, this just should show you kind of the enormous progress we have done over this time period. And this transfer learning concept really enables us nowadays to train on completely different tasks like medical images, these types of models. So why do we need AI for medical images? To now make the connection back to medical images. First and foremost, we want to improve diagnostics in medical images, which is a tedious and complex manual work task. So if I go to my radiologists, they take the scan, and then I need to wait a couple of days, if I'm lucky, until a doctor has manually checked my X-ray, made a diagnosis. And if I'm unlucky, but this can always happen, the diagnosis is not capturing everything, right? But this is the current process. But I can expect that this is a well-trained doctor who does this analysis. But one goal could be to speed up this process and to also improve this process. And I am always a big fan is because sometimes it's this discussion like, oh, AI could do errors, the human could do errors. Are we replacing human judgment with computer-driven automatic judgment? And I am always a strong, I have always the strong opinion that these two things should work together. So we can have a human-machine co-work. So for example, the human makes the judgment, the AI makes the judgment, the human looks, the doctor looks at the AI judgment. Does this match? Does it not match? Oh, maybe I missed this, or oh, maybe this is not correct, right? So I see it always in best case as some kind of cooperative work between human and AI. But there is also areas where it makes total sense to do a full driven AI prediction, for example. So one thing would be cross diagnostics across medical fields. So let's say there is a doctor who is expert in disease A, and another doctor, and she or he is expert in disease B. And now the AI could train on both experts, but can supplement the predictions of, or the diagnosis of Dr. A with an automatic driven prediction from Dr. B, who is expert on another disease. So kind of connecting different expertise areas within a model. And maybe even the most useful thing for this whole AI and medical images is that we need to think that sometimes in certain areas, they are well-trained doctors, but this is definitely not the case on a global scale. So medical screening is very expensive and often only available in certain developed countries. But we might want to support doctors in rural areas where they can take a picture maybe, but they don't have the expertise to fully judge these types of images and getting a full-fledged diagnosis. So probably somewhere in the US, there is an expert in a certain disease, right? And that person can make the diagnosis very well, but somewhere in a rural area, this might not be possible. And with AI, we could provide world-class expertise and scale medical efforts through technology. And I think this is beautiful in a way, and we can really strive to have full medical expertise across the whole globe. Yeah, and what I want to do now is that I want to go through one use case a little bit more step by step, and trying to outline the different steps I or also many others would usually take when they conduct these types of medical image-like problems. And I hope that I can motivate you to think about some of these steps and include it in your work. But this is just a rough outline of how I usually approach this problem. And obviously there is a slight difference from person to person. And with these use cases, I also want to give you ideas of applications for medical image diagnostics. The first one, and I heard that you already had some kind of presentation where similar task was mentioned, is about also a Kaggle competitions, which was called APTOS blindness detection. And in this task, the goal was to detect diabetic retinopathy to stop blindness before it's too late. And it is one of the leading cause of blindness in the working age population of the developed world. And it is estimated to affect over 93 million people. And this is also a use case where it is very useful to have this kind of diagnostic capabilities in rural areas. So it was a data set with thousands of images, and around 3,000 teams participated in this competition. And the first step, or step 0, when you start working on these types of problems, is usually to understand the problem. Like, what am I even trying to do here? And in this case, you have the images of the retina, and you need to predict this retinopathy problem classified into 5 different severity levels, which we have here on the bottom. So normal, mild, moderate, severe, proliferative, which is quite bad in the end. And according to medical literature, there are certain types of markers on the retina that indicate different stages of this disease. Like, how do the hemorrhages look like, heart exudates, abnormal growth of blood vessels, and so on and so forth. So just looking at this, I will try to build an image model that can look at an image of a retina and make identify different patterns in this image and try to predict the severity of this disease. And another important step in the beginning is also to understand the metric that you're using in order to judge your solution. And this is also for any type of business problem you ever encounter. This is something that is way more crucial than many people think, to find a good metric to measure your accuracy. So it is not always simple accuracy. In this case, it was quadratic weighted kappa, which you would need to research, but it is a certain type of metric, and I needed to research this when I first encountered it, which is a metric that works kind of well on these ordinal type of classes, because in this metric, it is better to, for example, predict moderate when it is actually severe versus predicting mild when it is severe. So kind of the difference in this ordinal type of classes, just as a side note. So yeah, understanding the problem, understanding the metric. The next step is to inspect the data and do explorative data analysis. So here on the left-hand side, we have of this data set, the distribution of classes. We can see that most of the images have class 0, so normal, no disease. And of those having the disease, it is class 0, class 2. Class 2 is moderate in this case. So we only have not too many very severe ones, and this kind of middle class is the most popular of the disease ones. And then we can also look just visually and qualitatively at a few examples of these different types of classes. So first row would be this normal, so no disease, and then we have for each row the different labels, samples from these different labels. And we can just already visually see it gets kind of worse and worse the further down we go here. So here on these images, you can see that looks already pretty bad, and probably visually. And I could already look at that and think, okay, that's quite bad, right? So maybe me personally, I would judge this as label 4. But here visually, it is already a bit more tricky, and hopefully a model can better capture these kind of granularities, what an expert doctor can. After we have looked at the data and did some explorative data analysis, an optional, and this is really optional because this is not always necessary, you can do some data pre-processing. So here in the original data, it is quite messy. It is coming from different devices, which is quite common in medical images, like one hospital versus the other has different devices, and they introduce different types of patterns into the image. And you might want to remove these patterns. So for example, and they might be differently cropped and centered. And what we did here is that we just center crop a circle on all of these images. And then they look kind of more similar. This is not always necessary. And actually, the neural networks are really clever, and they can work with messy data usually quite well. And you're also trying to counteract this a little bit with augmentations. We will get to that. But sometimes they can also, if they find a signal in the data, they will overfit to it if possible. So if there is, let's say, a big label of this is hospital A and this is hospital B on the image, and hospital A is doing only really bad cases, right? And hospital B is only doing really mild cases, then the model would say, okay, oh, there is always this marker of hospital A. I would always predict this is a more difficult case. And then you want to transform this to an unseen hospital 3 or C, and you will have an issue. So you need to think about these kind of spurious correlations, which might be present in the data. And if necessary, you might need to remove it beforehand or steer the model away from overfitting on these kind of aspects. Another thing we did here is to remove the blur. So our final input image looked something like this, but really this is optional, and the models can usually handle this kind of data really well by itself. So, and the third step, and this is oftentimes kind of jumped over, but I think this is one of the most important things in any kind of ML project. And the more of these kind of use cases you work on, the more you learn this, is how to do proper validation. Because what we are learning, right, is to build good models that can at some point be used in practice. And think about some doctor might have a platform in the end where there is the model in the back end and he or she uploads an image and you get the prediction out. And you want this also to work on really completely unseen data well. So you need to kind of simulate in your training process this unseen data. So what is the most simple thing to do is to split out, let's say 20% test data and 80% training data, train your model on your 80% training data and validate it on the 20% test data. But it is even better if you do this multiple times. So in this case, this is called cross-validation. And in this case, we would have a data sample of 12 and we would do 3-fold cross-validation. So we would split out this test data set 3 times. So first we shuffle the data and then we split this out 3 times. And of each of these 3 times, we train a model on the training data set, validate it on the test data set or validation data set, however you want to call it, 3 times. So you train 3 times on different data and validate 3 times on different data. But in the end, you validate on the whole data because you split out the first third, second third, third third. And then you get 3 times the metric. And this gives you a way broader perspective of the quality of your model. And in best case, you do this something like 5-fold is very commonly used, or even 10-fold. And this gives you more robust insights into the quality of your model. Of course, you can only do it once, but that kind of limits. And in some very large deep learning problems, you might need to do it because the runtime is so large. But if possible, I would always encourage you to do a 5-fold cross-validation, let's say. And you also, this is sometimes not enough, and you sometimes also need to think about leaks. So let's say you have multiple images of the same patient in your data set, right? But in the future, you will use it on completely new patients. So then you don't want to mix the same patient between a training set and the validation set, because the model will learn, oh, this patient probably has this type of disease and just predict it all the time. And it will do way better than it would do in reality on new unseen patients. So this is something you really need to carefully think about when you start to designing your experiment, is how to properly do the validation setup. The next thing is, so you understand your data, you have a validation data set, you want to build a baseline model and get started. And here really the first goal is to establish a training and validation pipeline. And this is also something I learned throughout the years. When I was beginning in data science, I was really, and it is a valid approach. It is like running a notebook here, preparing the data, then doing it here, then having mix-ups of versioning and stuff like this, right? This is how it oftentimes works. But for these machine learning projects, it is really valuable to have a full-fledged pipeline that you can run in, let's say, one notebook, or even better, one script, which would be something like the pipeline loads the data, processes the data, sets up the validation routine, trains the model, predicts on new validation data set, calculates the metrics, and even logs the metrics. And then this can really bootstrap you to experiment more and more, which we will get on the next slide. But experimenting is an integral part of any type of machine learning project. And the better and more robust your whole coding pipeline is, where you, let's say, okay, I want to change the number of epochs and see how that works. You just change one parameter, click on a button, and it runs the full pipeline and it logs the metric, and you're happy and see whatever impact it is. But if you need a couple of hours to just change your whole code, you lose track. And so really my advice here is to work on these pipelines, and you can reuse these pipelines across problems, and your own framework, in a sense, will grow throughout your career. And yeah, for a baseline model and for any type of these models here, we would use what we talked earlier about, which is transfer learning. So you pick a framework of your choice. Let it be PyTorch, TensorFlow. You can use any of the libraries that are out there. Fast AI, PyTorch, Lightning, I don't know, whatever you feel comfortable with, writing your own pipeline, using any type of library that is available. And then you pick a pre-trained ImageNet model, a certain architecture, let's say a ResNet model, an EfficientNet model. I will not go too much into detail here, but run your baseline model, and then when you have the results, you have a baseline score. And it is always great to have a baseline score, because that's what you can improve. And that's the goal of any machine learning project, of any supervised machine learning project. Okay, let's say your accuracy with your baseline model is 0.7. How high can you go? And that's kind of your reference point. Because then you need to start experimenting. You need to improve your baseline model. And hopefully you have this flexible pipeline where it is very easy now to try out different ideas. And logging is an integral part. So if you can build up your logging routine, like here on the bottom, I'm using a tool called Neptune AI, where here you could see 2 experiments, and I log different metrics throughout the epochs of your model training. And you can see, okay, this experiment, after I changed this parameter, this experiment was better. And okay, I will probably continue from this experiment. So this is really, you want to fail fast and iterate and iterate and iterate. And here on the top, you can see this Christmas tree, which is kind of a previous competition a colleague of mine did. We kind of depicted the different experiments we took and how this graph of experiments looks like. And you can see you start somewhere here on the left, you go a certain direction, you improve, then you have an idea. You're going another direction, let's say up here, and oh, it doesn't look that promising, let's go back and continue from there. And in the end, you end somewhere with your experiment where you say, this is what I'm happy with, this is what I will use for production, for submitting, for showcasing, for whatever it is. So really, machine learning is also an experimental science in a way. And I can always encourage you to really learn about how to properly experiment, how to build your pipeline, how you get a feeling of comparing these different types of models and experiments you run. And as a final note on this slide, just a few tips for tuning. So for quickly improving your model would be changing the learning rate of your deep learning models, the learning rate, the batch size, change the backbone, go from a ResNet to an EfficientNet, change the augmentations. Augmentations play a role. Augmentations mean that you randomly transform your training images while training to synthetically generate more images. So the simplest one would be you have an X-ray image, for example, and you flip it 50%, flip it horizontally, and you have a new image, right? It is still the same, but it is flipped. And if in future there is a flipped image, it might learn for this flipped image already. Yeah, and, image size and so on and so forth. So there's a lot to tune, and you get with experience, you know which kind of screws you need to turn in order to improve your solution. But starting with learning rate, batch size, backbone, augmentations can get you really far already. And you have your baseline model. You can see how well it improves. The next step is ensembling. So this is a concept where you try to combine predictions from different models, and this can significantly boost the performance of your models. So you have run different experiments, right? And your final 2 models is one is with augmentation A and the other one is with augmentation B. So what you can do now, and both of them are kind of working well, but they are diverse because they use different augmentations, let's say, or different backbones or different image sizes. Something should be a little bit different, but they are both performing well. And some of those models might be doing well in certain areas of the data, and others might do well in other areas of the data. So what can you do? You can just take both and average them. This is the very simplest format of ensembling. So if one predicts 0.5 on one record and the other 0.7, you can just average it and say, my prediction is 0.6. So this is called simple blending, where you just average the predictions of multiple models. And this works really, really well in practice. So never forget that you have the chance to do this. There's more complex ensembling in the area of stacking. I will not go into detail because from my experience, and I'm actually mostly doing blending, this works specifically in deep learning like problems really well. To just average different types of models and check how well that scores on your validation data set. Yeah, and the final step of this project is to report, deploy, iterate, right? So after a model is before a model. The dream, at least to me, of every kind of deep learning or machine learning or data scientist, practitioner, is that your models get used in the wild, right? If I build a medical diagnostic model, my dream would be that the doctor actually uses it and it has an impact. So how can we bring it to this point? Now you have your Jupyter notebooks, your Python code, and you will not ship this to a doctor and saying, type in Python predict.py, right? So you need to also think at the end of your projects about how you can make this available. So there's this whole area of how to deploy the models, how to communicate your results to stakeholders, and this might also play a role in the data fund, how to properly present the results in the end. Probably not so much about productionizing, but in industry, this is very important. And then iterate. So this process is never finished. You will get feedback. You might need to tune your model again based on this feedback, might incorporate new data that comes out. So this is a whole, always see this as an iterative process. And yeah, here on the bottom for this problem, a colleague of mine built a very simple application in H2O Wave no-code framework, which is just a framework to build this type of AI applications, where someone could upload an image and you get the predictions directly visualized here. So you upload this image and the application would say, this is moderate. My model is predicting moderate. So very simple applications, and you can build these type of applications after your model building process. So yeah, be aware that this is also a part of data science and machine learning. So yeah, this was our first use case, and I went step by step. Hope you're not overwhelmed, but this is kind of just my experience and kind of advice to everyone doing these type of projects of certain types of steps. And of course, for each problem, there is a certain special thing you need to care about and might divert from problem to problem, and obviously about also depending on the time you have available for this project. So now I just want to cover a few more use cases without going technically too deep, but to maybe give you a few more ideas about what type of medical use cases are common. So now we captured this retina issue, and of course, maybe the most well-known is anything about X-rays. And there are also a lot of public data sets available surrounding mostly chest X-rays. So this was a competition I did not long ago, which was about X-ray abnormalities. And here you need to detect abnormalities in chest X-rays, and it is to reduce the pressure on doctors at metropolitan hospitals and improve diagnostic quality in rural areas. And this was not a classification problem, but now an object detection problem. So object detection is another type of computer vision like problem where you don't have an image and say, this is a bad image, this has this diagnosis, but you rather try to predict areas in the image, boxes, with some certain artifact. And in this case, it was a multi-class object detection task. So you need to predict certain patterns, so certain abnormalities, and also the box. And you have different types of abnormalities. So this is the ground truth data. So for example, this would be a box for aortic enlargement. And you need to say, this is the box for this type of disease or abnormality. This is where it is. And this is also what class it has. So your model could make a wrong class prediction or a wrong box prediction. So this is a rather more advanced task, I would say, and also way harder task than simple image classification or regression. but it can be a very, very useful task for doctors, because they don't only get the prediction, but they also get kind of the areas of where the model thinks this type of disease is present. And again, just one slide for a rough overview of our solution. The first thing we did here, and this is also something you need to care for most of the medical image data sets, is that the data quality sometimes is very dependent on who annotated it. We talked about expert doctors and non-so-expert doctors, and this also manifests itself in this data set. So there might be a different quality in annotations, and what was here important was to weight the annotators a bit differently based on how well their labels, their training labels were. And again, here you use for object detection, the process is very similar. It's just a different task, but you still use state-of-the-art detection models that have been pre-trained on some other data set. So it is still transfer learning. The most well-known are YOLO v5 and EfficientDet. We also use for our solution here both of them. And again, ensembling is very important, but now you cannot say, oh, I average just the predictions, but you need to also average the boxes. So here on the right-hand side, you can see an example. So let's say you have 3 models here, and model 1 would predict one blue box, the second the other, and the third the other. And now you want to find a consensus between these boxes. There is the most common technique is called non-maximum suppression, NMS, where you just take the one with the highest confidence. But there is one that is used heavily, also specifically on Kaggle, and it is doing really well, which is called weighted boxes fusion, where you try to really merge the boxes together to build a new box. Yes, so again, every other step I told you for this other problem completely applies here, but I didn't go into detail again. But it is just a different type of problem and a different type of model you want to use, and a different type of ensembling technique, and maybe different type of pre-processing. But the whole pipeline flow is in general quite similar. You train a model, you build a baseline model, you try to improve on that model, you measure the metrics somehow, you find the validation setup, you build your pipeline. So this whole data science process is the same. There was also a recent competition, again, chest X-rays, which I just want to mention because it fits, unfortunately, the current times, which was about COVID-19 detection, where the goal was to identify and localize COVID-19 abnormalities on chest radiography. So we had to predict it as negative for pneumonia, or typical, indeterminate, or atypical for COVID-19. And it was kind of a combination of classification and object detection. So both tasks at the same time. And here you see some examples for like these different categories of typical, negative, and indeterminate. So also interesting task where a lot of good can be done by solving it. And the final task I want to mention, and for chests, really, you can find a lot of the data sets online, also browsing through Kaggle, old Kaggle competitions. And the final one is, again, a bit different, to not only have chests, but is about melanoma classification, where the goal was to identify melanoma in images of skin lesions. And as with other cancers, early and accurate detections are potentially aided by data science can make treatment more effective. And we had thousands of training images, and this is probably the most simplest type of problem in the sense, not simple, but in terms of setting it up, is about binary classification. So either the goal was detecting whether this image has a benign melanoma or a malignant, so a dangerous melanoma. And again, here, I have no slide for solution, but basically think about, again, whole pipeline, just transfer learning, and solving this with pre-trained models, and augmentations are really important here. Yeah, some more interesting problems just for inspiration, potentially. There is also the area about detecting neurological disorders. We talked about image classification, We talked about image object detection, but there is also image instance segmentation as a problem type. So instance segmentation is not about predicting boxes, but areas. So it would be real areas of certain types of diseases, for example. There was also, going back to the X-rays, there was also interesting data set for X-ray catheter and line position. So you get a catheter and a line and it takes the scan, and you need to predict, is it correctly positioned or not? There's also one for detecting pulmonary embolism, blood clots in chest CT scans, now CTs. So there's also medical imaging. There's also sometimes 3D data instead of just 2D data. And the final one I want to mention is to predict lung function decline. This was a regression problem. So we already are close to the end, just a few kind of learnings from my side. So what did you learn today? So for medical diagnostics, one thing I mentioned is that data quality plays a crucial role. So check the consistency of labels, search for additional data sets online. More data can oftentimes be really useful. We talked about transfer learning. Transfer learning really, really works. And this is the beauty nowadays, that you can fit on new types of problems that no one else has solved before, but take these kind of pre-trained models to really bootstrap your results. And augmentations can be important. We haven't talked too much in detail about certain types of augmentations, but from my experience, cutout is usually very important. Augmentation, affine transformations, mix-up cut mix, which is about mixing different images together to build new images. But specifically for chest X-rays, augmentations are very, very hard. It is very tricky, just for you to note if you work with chest X-rays. More general learnings is, we talked about understanding a problem and data and finding good validation setups that can generalize well to unseen data is crucial. I tried to emphasize a lot that setting up robust training and validation pipelines can be very helpful, because it really accelerates your experimenting steps. And there is so much information now. I'm just telling you a very small set of things, but there is so much research and other people addressing these problems in the past. So research old solutions to a problem, check papers, check Kaggle. Kaggle is really a great resource for reading through solutions, what other people did. There are a lot of public notebooks with baseline solutions. So you could start from that, for example. There on the web, you find in blogs, you find so much information. So go out there and research what has been done. You don't need to start oftentimes from scratch. Yeah, we talked about experimenting a lot and iterate quickly and never be discouraged. Failing is part of the effort. So failing is a good thing, because you know, okay, you tried it and it didn't work. So another direction is maybe the more promising. Yeah, so with that, thanks for your attention. And if there are any questions, we can